We will now evaluate the integral minus infinity to plus infinity x sin x dx by x squared plus 1 into x squared plus 4 using contour integrals. Okay. So in this case, how do you integrate this? So now what you will do is, we will consider integral over c z e power I z dz by z squared plus 1 into z squared plus 4, where c is the upper half of the complex plane semicircle with the radius r. So now what I have done, I have just replaced x with z. Suppose if I assume f of z as z e power I z by z squared plus 1 into z squared plus 4. Okay. If I want to find the value of this integral, I have to use either Cauchy's integral formula or residue theorem. Better will be Cauchy residue theorem. If I want to use the Cauchy residue theorem, I have to find the residue of the function f of z. If I want to find the residue of the function f of z, I should first find the singularity of f of z. So singularity of f of z is f of z r. I'll have z squared plus 1 into z squared plus 4 is equal to 0, or from this z is equal to plus or minus I plus or minus 2i. So z is equal to I and z is equal to 2i lie inside C, because you can write I as 0, 1 and 2i as 0, 2. When you take the real axis, x-axis as the real axis and y-axis as the imaginary axis, 0, 1 will be here, 0, 2 will be here. So in this case it will lie in the upper half of the plane. Now what you do is you choose the semicircle such that these 2 points lie inside C. And you can see that both are simple poles because it is of order 1. Okay. So now what you have to do is you have to use the appropriate formula to calculate the residue. So first what I do is I calculate residue of f of z at z is equal to I. This will be limit z tending to I, z minus I into z e power I z by z plus I into z minus I into z squared plus 4. Okay. So now what I will do is z minus I gets cancelled here. So I'll have I e power minus 1 by 2i into minus 1 plus 4. Okay. I gets cancelled here. Okay. So I'll have 1 by 6e. Okay. And similarly, residue of f of z at z is equal to 2y. This will be limit z tending to 2y, z minus 2y into z e power iz by z squared plus 1 into z minus 2y into z plus 2y. Okay. So now z minus 2y gets cancelled here. and when I substitute 2y, I will have 2y e power minus 2. Okay, by this will give you minus 4 plus 1 into 4i. 2i and 4i gets cancelled here, giving you 2. So this will give you minus 1 by 6 e square. So one of the values will be plus 1 by 6e and the other value will be minus 1 by 6e square. So now what I will do is I will use the residue theorem. When I use the residue theorem, I will have integral over c z e power I z dz by z squared plus 1 into z squared plus 4. This will be 2 pi I into 1 by 6e minus 1 by 6e square. Okay. So now this will be, if I want, I will try to simplify this. Before that, I will write integral minus r to plus r. Because it lies on the real axis, I will have x e power ix dx by x squared plus 1 into x squared plus 4 plus integral over cr f of z dz. This will be pi I by 3e into 1 minus 1 by e. Okay, because when I remove this 6e, I will have 1 minus 1 by e. 2 by 6 will give you 3 in the denominator. And now what I do is I allow r to tend to infinity. Okay, so when I allow r to tend to infinity, now what will happen to this? Modulus of integral over cr f of z dz. This will be less than or equal to integral over cr mod z mod e power iz mod dz by modulus of z squared plus 1 into modulus of z squared plus 4. This will be less than or equal to capital R for mod z. And modulus of e power iz will be 1. Mod dz will be length of the curve pi r by this will be r squared minus 1 into r squared minus 4. I will have r power 4 in the denominator, r squared in the numerator. So when r approaches infinity, the value of this integral becomes 0. So now when I allow r tends to infinity, this part will become 0. So I will have integral minus infinity to plus infinity x into cos x plus I sin x dx by x squared plus 1 into x squared plus 4. This is equal to pi I by 3 into 1 minus 1 by e. When I equate the imaginary parts, I get integral minus infinity to plus infinity x sin x dx by x squared plus 1 into x squared plus 4. This will be pi by 3 into 1 minus 1 by e. This completes this particular problem. So in this case, what you do is you replace x with z, take the contour as the upper half of semicircle in the upper half of the complex plane, use the residue theorem, and then according to the problem you equate either the real or imaginary parts that will give you the required solution.